Hello everyone, I'm Jie. Today I'm going to present our paper, TVR, a large-scale dataset for video subtitle moment retrieval. My collaborators are Licheng, Tamara, and Mohit. We are from UNC Chapel Hill. TVR is a multimodal retrieval dataset. It is unique as it requires system to understand both videos and their subtitle text. Here we show a TVR example. The query is, Rachel explained to a dad on the phone why she can't marry her fiancé, and the matched moment is,
Daddy, I can't marry him. I'm sorry. I just don't love him. Well, it matters to me.
As we can see from this video, the part on the phone is more related to the video content, while the part explained to her dad why she can't marry her fiancé is more related to the dialogue subtitle. Thus, to more accurately localize this query, a system needs to comprehend both the dialogue subtitle and the video content. To collect those queries, we present annotators a 60 seconds long video with associated dialogue subtitles to encourage them writing queries that requires both modalities. They are required to find an interesting moment in the video and mark its start and end, and then write a query that describes the marked moment. In addition, they are also required to mark the type of the query, whether the query is more related to the video or subtitle or both. To collect high-quality annotations, we adopt the following collection procedure with a set of checks and tests. At step 1, we use a qualification test of 12 questions to make sure workers understand our requirements. At step 2, qualified workers from step 1 perform annotation following our instructions. And next, at step 3, our automatic checker performs basic checks, such as whether all the blanks are correctly filled and the description is at least 8 words long. At step 4, we perform in-house manual check of the queries. Disqualified queries are re-annotated, and the workers with disqualified queries were removed from our work list. Lastly, at step 5, to verify the annotation quality, we also performed a post-annotation verification experiment. With this strict data collection procedure, we collected 109K human annotated query moment pairs on 22K videos, making it the largest dataset of its kind. TVR is the only moment retrieval dataset that requires both video and subtitle context, and it is also the only one with query type annotations. These query type annotations could be used for deeper analysis of the dataset and the model that built on top of it. We show distribution of TVR query type on the right. In addition, it also has a much larger vocabulary size, making textual understanding challenging. Compared to existing datasets, TVR has relatively shorter video length normalized moments and longer queries. Here we show the percentage of queries that have multiple actions or involve multiple people. Compared to existing datasets, TVR queries typically have more people and actions and require both video and subtitle context. Our task is video corpus moment retrieval. Given a natural language query and a large video corpus, our goal is to retrieve the matched moment from the corpus. It requires not only retrieve the ground truth video, but also localize the moment from the retrieved video. To solve this task, we propose cross-modal moment localization, XML model. It performs video level retrieval at its lower layers, and fine-grained moment level retrieval at its deeper layers with a novel convolutional start and end detector module. Scores from both sides are aggregated together to generate the final scores. Our XML model first encodes the query sentence using transformer encoders. The encoded embeddings are then aggregated with two trainable weight vectors to generate two modularized query vectors for video and subtitle respectively. For context, we extract pre-trained vision and language features, and then encode them using transform encoders. We use lower layer features for video level retrieval, and we use deeper layer features for more fine-grained moment level retrieval. We compute video retrieval score by computing scores for each modality, and then average them together as the final score. We train video retrieval with the ranking laws. For single video moment retrieval, we first compute query clip similarity scores within a product. We then apply our conv-SE module, which are essentially two 1D convolutional kernels, to detect the start and end edges in the similarity score curve. The intuition here is that the clips inside a semantically closed span will have higher similarity to the query than those outside, naturally form detectable edges around the span. The filter scores are then normalized with Optimize to output probabilities of each position being the ground truth position. This module is trained to maximize the scores of the ground truth positions with cross-entropy. To generate corpus-level scores, we aggregated the video retrieval scores and the moment-level scores together. We split TVR into 80% training, 10% validation, and 5% test public for reporting at our public leaderboard, and another 5% test private is reserved for future challenges. We use required K as our metric. A prediction is correct if the predicted video matches the ground truth video, and the predicted moment span has high intersection over union with the ground truth span. Experiments show that our proposed XML model outperforms previous baseline method by a large margin, and with better efficiency. Here we show performance of XML models that use only video, subtitle, or both as inputs. We can see from the figure that using both video and subtitle performs the best, which indicates that both video and subtitle are important for this task. Here we show performance breakdown of XML models on different query types. For queries that are labeled as video-only model performs better than subtitle-only model. And we will reach the opposite conclusion when we look at the performance on subtitle-only queries. Here we show the performance comparison of moment generation methods under the same XML backbone. TAG and the sliding window rely on handcrafted rules, while conv-SE learns from data for more accurate localization. The results show conv-SE performs consistently better across different IOU thresholds. Here we show examples of the learned conv-SE filters applying on query clip similarity scores. The filters output stronger responses to the up and down edges of the score curves and thus detects them. Interestingly, the learned filter weights are similar to the edge detectors in image processing. Here we show two XML prediction examples. We see our model is able to correctly localize moments using both video and subtitle information. Additionally, we also found the XML gives higher modular attention scores to visible lines when the input is video. For example, in the top left corner, we see waitress, restaurant, and menu receives higher modular attention scores. For subtitle, words that are related to the dialogues are given higher scores, such as Rachel and the menu. Our TVR dataset and code are publicly available. We also collected additional description for each TVR moment, forming a new multimodal captioning dataset named TVC. In TVC, systems have to use information from both the dialogue subtitles and the videos to generate captions. For both datasets, we host public leaderboards to better compare the methods. Thanks for your attention.